1 minute before the start of the session, so let me introduce. So this is a session for the mathematical assumptions, and I'm Takahiro Matsuda from AIST, the session chair of this session. So the first talk of this session is the one-wayness of Jacobi signatures, and the authors are Henry Corrigan Gibbs and David J. Wu, and the speaker is Henry.
Great.
So okay, let's start from 9:20.
We have 30 seconds.
Yeah.
Let's see. I could steal an extra 30 seconds for the talk, but
Yeah, maybe. Then okay, maybe.
It's like a reward for getting up early, right?
Okay, please start.
Okay, but what if they miss the first 30 seconds? It's like the best. Okay. Anyway, so my name is Henry, and this is joint work with David Wu. So to set the stage for this talk, we have to go back to 1988 when Windows 2.1 had just been released. Jackets like this were cool, and one of the most popular songs was, I don't know if you can guess it. I just had to put that in there. Literally, that was true, 1988. But more important than all of that, Damgard at Crypto introduced this PRG construction that I'll call the Jacobi PRG. And if you don't know what a Jacobi symbol is, I'll try to explain it in a second. But for those who do, I just wanted to refresh your memory on this construction. So it's parameterized by a big integer n and an output length L. And the PRG just takes as input a seed x, and it outputs the string of L Jacobi symbols, mod n, starting from x. So the symbol of x plus 1 mod n, x plus 2 mod n, and so on. And that's the whole construction. More recently, people have looked at kind of a PRF analog of this, where x is actually the key, the input is a value a, and the output of the PRF is the Jacobi symbol of x plus a mod n. So before I get into the results, I just want to give you some sense of why we were interested in this, why you maybe should be interested too. First of all, the PRG construction is super simple and arithmetic. So I just showed it to you on half a slide. And it's also very closely related to these MPC-friendly Legendre symbol constructions, Legendre PRF, PRG, and so on, that people have been using for post-quantum signatures and zero-knowledge proofs and oblivious PRFs. There's actually a post-quantum signature paper here that uses the Legendre PRG. And the last thing is that the security picture here is actually quite murky. So even though this is an old construction, we know things like the PRG passes statistical tests, but the best attacks we have are still exponential time. And even in the quantum setting, the polytime attacks require kind of oracle access to the PRF, and they don't apply to the PRG at all. So the bottom line is there's no known relation to any number theoretic assumption, no known relation for any of these constructions to any sort of existing assumption so far. So with that, our two results are the following. So first, we show that if factoring numbers of the form p squared q is hard, and a certain number theoretic conjecture holds, then this Jacobi PRG modulo a number of the form p squared q is actually a one-way function. So we can't show pseudo-randomness yet, but we show one-wayness at least for this construction. And this factoring special numbers of this special form is a problem that's been around for quite a while. The second thing we show is that if factoring is easy, then no matter what modulus you pick, as long as it's a composite, then this Jacobi PRF is actually broken as a PRF. Yeah, so the rest of the talk, I'll first give a little bit of number theory refresher, the stuff you'll need to understand the construction. And then I'll go through these two results. And I hope that by the end of the talk, you'll understand kind of the technique of proof for both of them. So if you haven't seen it before, refresh your memory, it's defined for primes with a prime modulus. And the Legendre symbol of x mod p, which I'll denote like this, just takes on the value 1 if x has a square root mod p, or is a quadratic residue, and takes on the value -1 otherwise. And this function is efficiently computable via this just x to the p minus 1 over 2 mod p gives you the Legendre symbol of x mod p. So once you have that, the Jacobi symbol is just the product of the Legendre symbols modulo each prime factor of the modulus. So the Jacobi symbol of x modulo p times q times r is just the Legendre symbol of x mod p times the Legendre symbol of x mod q times the Legendre symbol of x mod r. That's all. And it turns out via a different algorithm, you can compute the Legendre symbol of x mod n for a composite n without knowing the factors of n. So that's a fact. I won't explain why that's true. Okay, so just to go back to the PRG construction, now that we have that background, the public parameters are kind of a lambda bit integer n, which is probably going to be a composite, and a output length L, which is going to be polynomial in the security parameter. And then the seed is just a value in Zn star, and the output that I'll denote G sub n comma L is just this string of L Jacobi symbols starting from X mod n. And I'll use that G notation for the rest of the talk. So the Legendre PRG, which you may have heard of, is just the same thing where the modulus is prime. And one little distinction is that in Demgaard's original construction, actually the modulus was secret. And most people when they're using this thing, actually treat the modulus as public. So for this talk, I'll focus on the public modulus setting, but our kind of security result implies security for the secret modulus setting also. So we proved the stronger result. All right, the last piece we need is this Bonnet-Lipton conjecture, which is just a number theoretic conjecture that has nothing to do with crypto. And what it says is that for any prime p, this string of Jacobi symbols or Legendre symbols, mod p, if you stretch it out long enough, so like log squared p symbols, that output actually determines the seed. So if I give you the output of this PRG, if I give you enough bits of output, that actually fixes the seed exactly. So there are not two seeds that produce the same output. I think one thing just to note, this conjecture should be very challenging to prove, in part because it implies that the least quadratic residue, modulo every prime p, is bounded by order log squared p. In that problem, bounding the size of the least quadratic residue is very old. And we only know this kind of bound assuming the Riemann hypothesis and things like that. So we won't expect to prove this unconditionally. All right, so those are the two pieces of background that we need. Now let me get into the proof of the first result. So again, this is that if factoring numbers of the form p squared q is hard, and that conjecture holds, then the PRG construction is actually one way. Yeah, and I should warn you, these are not going to be very complicated proofs, so I hope you're not disappointed. I guess depending on your point of view, you could actually be excited by this fact. People have different opinions, but either way, they're simple. So I hope by the end of the talk, you'll actually understand the proofs start to finish. Okay, so this is the first thing we're trying to prove. And the strategy is just going to be a direct reduction. So we'll show if you have an efficient Jacobi PRG inverter, I can give you back an efficient factoring algorithm for numbers of this form. And that implies immediately that if factoring is hard, then there can't be such an inverter, and this PRG is one way. So the main trick we use is that when the modulus n has this special form, then the Jacobi symbol mod n, via this sequence of identities based on how the thing is defined, is actually equal to the Legendre symbol of x mod q, mod one of the factors of n. So even without knowing what q is, you can efficiently compute the Legendre symbol of x mod q via computing the Jacobi symbol of x mod n. So that's kind of one of the key tricks. So with that trick, I can actually show you how this proof works. So this is, again, going to be showing that if I have a Jacobi PRG inverter, I'll give you a factoring algorithm. So here's how the direction works. Our factoring algorithm is going to take as input a factoring challenge, so a number of the form p squared q. And the factoring algorithm is going to sample a random seed for this PRG. And then it's going to produce this PRG output. So it's going to give the Jacobi PRG inverter the modulus n, and this string of Jacobi symbols mod n of x plus 1, x plus 2, all the way to x plus something like log squared n. And the reason this factoring algorithm can cook these up without knowing the factors, again, is because the Jacobi symbol is efficiently computable. All right, so our inverter is going to give us back some seed that explains this output. Seed will be, call it x prime. And I claim that if the factoring algorithm outputs the greatest common divisor of x minus x prime with the modulus, that actually reveals a factor of the modulus itself, so reveals q. But this is it. That's the whole reduction. And now I'll try to explain to you why this should work. So the proof is in two steps. The first thing we show is that this value x prime that the adversary gives us back is actually congruent to r seed x modulo q, mod this second factor of n. The reason why that's true is that the outputs of this PRG on x and x prime have to be equal. That's kind of what it means to invert this PRG as a one-way function. And then since this modulus has a special form, it means that the output mod n, the output mod n is congruent or is equal to the output mod q. So the fact that the PRG outputs are equal mod n also means they're equal mod q. And then by the Bonnet-Lipton conjecture, if they're equal mod q, then they have to be equal themselves, because there's kind of only one output that can explain this, this string of Legendre symbols. So that's the first step. They should be congruent mod q. The second step is that they should be different modulo p or modulo p squared with extremely high probability. And the reason for that is, again, by the special structure of this modulus. Since the Jacobi symbol of x mod n is equal to the Jacobi symbol of x mod q, the adversary's view is actually completely independent of p. It's independent of x mod p. So the adversary has no information about x mod p. So when it gives us back an x prime, it's sort of independent of our choice of x modulo p squared. So the probability that it gives us back an x prime that's congruent to our x mod p is very, very small, is negligible. Okay, so then the very final step is to say, look, if x and x prime are congruent mod p, then it means that x minus x prime is 0 mod p, or x minus x prime is a multiple of p. But it's not a multiple of p squared, because these two things are different mod p squared. And then the GCD of this value with n has to be q, right? It's a multiple of q. It's not a multiple of p. So the GCD with n has to be this factor q. And that's it. So what's the consequence of this? So first, a total break of this PRG would be very surprising, because it would imply a factoring algorithm for numbers of the special form, which is a pretty old problem, well studied. There's actually even a paper in this year's ANTS that looks at factoring numbers of this form. And still, as n grows very large, the kind of general factoring algorithms are the best we have for this kind of number. A very similar argument that I'm not going to show shows that this PRG is actually collision resistant under a new and stronger number theoretic conjecture. So some things that it doesn't show. So first of all, we don't know if you have a factoring algorithm, can you break the PRG? That direction, we have no idea. Would be super interesting to know. We also don't know if the PRF is secure under factoring. So this kind of result only applies to the PRG. And I should say the PRF modulo prime. We don't know if that's secure under factoring. Okay, so then the second result is that if factoring is easy, then the PRF modulo a composite is broken. And this I think is even more direct. So let me remind you what the PRF construction is. So this is, again, the modulus is some lambda bit composite. The key is just a value in Zn star. And then the PRF output is just the key x plus whatever the input is, modulo n, the Jacobi symbol of that. So the Jacobi symbol of x plus a mod n. And the security notion is the standard one for pseudo-random functions. It says that an adversary shouldn't be able to distinguish oracle access to this Jacobi PRF with a secret key x versus oracle access to a truly random function with the same domain and codomain. Cool. So I won't give the full kind of proof result here. I'll just give you the intuition for how this works. The main idea is that when n is a composite, polynomials mod n, the ring of polynomials mod n, doesn't have unique factorization. So in particular, if you have the factors of n, you can find a value r such that x minus r times x plus r is a formal polynomial, is equal to x plus 1 times x minus 1. So this polynomial x squared minus 1 actually has two different factorizations, mod n. What that means is that since these Jacobi symbols are multiplicative, it actually means that for every key x, if you evaluate the Jacobi PRG on 1 and multiply that by the PRF on 1 and the PRF on -1. You multiply those things together. And you take the PRF on R and the PRF on -R, and you multiply those things together, you'll get the same value always if you're interacting with the Jacobi PRG. Whereas with a random function, this kind of relation will only hold with probability 1/2. So this only requires 4 queries to the PRF and distinguishes with constant advantage. So that's like a total break when you can factor. So this implies kind of a sub-exponential classical attack via factoring, and then a quantum polynomial time attack, again, via factoring. I'll say this doesn't actually affect the PRG construction at all. And the reason is the only way you can kind of identify this relation is by making very special correlated queries to the PRF. And if you're just given some PRG output, the chances that you'll kind of be able to test this kind of relationship is very, very small. So still the PRG, if we know how to factor, we don't know how to break the construction. All right, so in the last few minutes, I will sort of mention the open questions that are most related or that we're most interested in. So first, we don't know how to prove one-wayness even of this PRG, assuming that factoring numbers of the normal form, like P times Q, is hard. We're somehow very much relying on this P squared Q business, which is somehow feels artificial. We also don't know how to remove the dependence on this number theoretic conjecture. It's not clear that we should need that to prove security, but our sort of approach seems to require that kind of thing. More generally, I would be really interested in seeing a sub-exponential time attack on this PRG. So we know we have some better than kind of brute force exponential time attacks, but we don't know if there's some kind of clever index calculus technique you could use to do something better. And in addition, it would be really nice to find kind of a clean sigma protocol for proof of knowledge of a seed that explains some output. So proof of knowledge of a preimage of some output of this PRG. And sort of a clean proof of knowledge, a very simple sigma protocol, could potentially give you a very nice post-quantum signature scheme from this type of assumption. Okay, so just to wrap up, the landscape before this work kind of looked like this. For any of these properties of these Jacobi functions, whether the modulus is secret or public, we didn't know how it related to other number theoretic assumptions. So this paper gives us 2 things. So again, the PRF with the public modulus is easy as factoring when the modulus is composite, and one-wayness in either the secret modulus or the public modulus setting, provided the modulus is composite. So I just wanted to finish by saying we have one very recent result on this, which shows that the PRG, when the modulus is secret, is actually as hard as quadratic residuosity. So it's pseudo-random under the QR assumption. And that's whether the modulus is composite or prime. So if you're interested, check out that paper. And yeah, I'll finish there and take questions. Thanks so much.
Any questions or comments from the audience? If you have, then please come to the microphone. Oh, yes, please.
Very nice talk, thanks. On removing the dependence on Bonnet-Lipton, does your existing proof work if you just have some kind of like relaxed average case version of Bonnet-Lipton?
Yes.
Okay, so it's more about the average case.
Yeah, absolutely. So just to clarify, so the Bonnet-Lipton conjecture says for all primes P, these outputs, the output of the PRG needs to uniquely determine the C. It's totally enough to say that for a constant fraction, say of primes P, that thing is true. And yeah, that would be fine too. But even that, it's not, at least to us, obvious how to show. Good question.
Other questions or comments? Please. Oh, you.
Thanks.
You have to work for it.
Is it pretty obvious how to break the PRG if it's just a prime modulus? Or
No.
okay, so the composites could be doing nothing.
Say again?
For the PRG, if it's just mod P and you do the Jacobi,
yeah, no,
it might be secure.
Exactly, and that's what people are using for post-quantum signatures is the prime modulus case, because there's sort of no secret setup that you need for that case, and so people conjecture that thing is exponentially hard to break.
So all these composites could be just for not. In
yeah,
sense.
yeah, in that sense, yeah. Although I should say the PRG mod composite is just the XOR of kind of two PRGs mod primes. So as far as the PRG goes, it's not worse to be monocomposite.
Oh, sure, but it might not be doing that.
Yeah, that's true. Yeah, good question.
Okay, other questions or comments? So let me have just a brief.
Sure.
So if you can your second result affect the weak PRF security of the Jacobi PRF
No, it just affects strong
No.
PRF security.
or ordinary?
Yeah,
security?
yeah, exactly. Because the adversary has to make correlated these sort of special queries to the PRF to be able to distinguish. If you're just given the evaluations of this PRF on random points, attack definitely doesn't work.
Okay, thank you. So since we are time up, so
Cool.
let's thank the
Yeah, thanks so much.
engineering. So the next talk of this session is generic and algebraic computation models when AGM proofs transfer to the GGM. And also the Joseph Yeager and Deep in the Mohan, and Deep will give a talk. Okay, please start.
Hello. Hey, everybody. Today I'm here to present our talk titled Generic and Algebraic Computation Models. This is joint work in collaboration with Joseph Yeager at Georgia Tech. So this work falls in a domain that we like to call meta-cryptography, since we're not really analyzing any specific cryptographic constructions, but rather the idealized models used for these constructions. With that, let me give you a brief background into what the problem is and how we're solving it. So when it comes to idealized models for group-based cryptography, the de facto choice for the longest time has been the generic group models by Shoup and Maurer. Now, the generic group models idealize cyclic groups, which means that they only restrict attention to the class of adversaries that interact with these groups in a black box manner. On the complete other side of the spectrum lies the standard model, which captures the reality that in the real world, these constructions have to be concretely formalized with actual representations of these groups, in which case these adversaries can use these representations, which could be, say, points on ZP or points on an elliptic curve, to exploit certain internal structures of these groups and come up with faster attacks against certain constructions. Now, the AGM assumption that the algorithms are completely agnostic to the choice of the underlying group is a fairly strong assumption. So in 2018, Fuchsbauer, Kiltz, and Loss, whom we'll hereby refer to as FKL, came up with the algebraic group model. Now, the AGM, like in the standard model, gives the algorithms access to concrete representations of the groups and group elements, but similar to the GGM, they are still in some ways restricted on what computations they can perform on these group elements. In this way, while being a stronger idealizing assumption than the standard model, the AGM was thought of as a weaker alternative to the generic group model. FKL further formalized this notion by providing a lifting result, showing how certain security statements made within the AGM could carry over directly to the GGM for free. This, in combination with the fact that the AGM allowed for simple reduction-based proofs, generally made cryptographers very happy. But alas, happiness is temporary. A recent analysis of the AGM by Katz, Zhang, and Zhou revealed certain problems with the GGM. They had some philosophical critiques with how the AGM by FKL was formalized, but the biggest result was a technical critique, which was a counterexample against the AGM to GGM lifting result. Now, without this lifting result, the AGM was left in a state of flux, and this made cryptographers fairly sad. KZZ suggested that future analysis should focus on specific settings where this AGM to GGM lifting result might hold, and there needs to be a more concrete analysis of the relationship between the AGM and the GGM. This is pretty much what we do. So more specifically, we come up with a new framework to express group-based algorithms, and our framework allows you to capture GGM, AGM, and standard model algorithms in a unified manner. As a consequence of our framework, we directly resolve all the philosophical critiques that KZZ have with the FKL AGM framework. And not only this, we also formally restored the lifting result from the AGM to the type safe or Morris GGM. And this lifting result actually falls out as a direct consequence of the way we specify our framework. So with that out of the way, let's get into some background, starting with what the generic group models are. As stated before, the generic group model idealizes cyclic groups, which means that it assumes that adversaries within the generic group models interact with the group in a generic manner. So this is generally formalized by giving these adversaries access to the group elements in some hidden format, and then by assuming that the adversaries can operate on these hidden group elements using some black box oracle functionalities. So a black box oracle for carrying out the group operation and then testing the quality of these hidden group elements. Now, proofs in the GGM are generally presented as combinatorial arguments, unconditionally relating an adversary's probability of success with the number of oracle accesses that this adversary has to make to these black box oracles. So for instance, you can show in the GGM that a generic adversary against the discrete log game wins with an advantage bounded by at most m squared over p, where m is the number of oracle accesses it makes and p is the order of the group. Now, I stated that the operations themselves are hidden by these black box oracles. But how do you hide the group elements themselves? Generally, in literature, there are two main choices for this, which lead to two paradigms for the AGM. The first option is to encode these group elements as some random bit strings, which means picking some kind of a random encoding function mapping from the group to bit strings and representing each element as the random bit string internally within your algorithm and using these bit strings to interact with the oracles. The second option is to assume that there exists some kind of a hidden table that stores all these elements, and then the algorithms can dereference these elements using the indices of this hidden table to the oracles. We can also assume then that the hidden table is updated lazily, which means whenever an oracle outputs an element that doesn't actually exist within the hidden table, it will first add that element to the hidden table and return the corresponding index. Now, the first paradigm is generally referred to as Shoup's formalism of the GGM or Shoup's GGM. And the second paradigm is Maurer's GGM, which Zandri in his later analysis also referred to as the type-safe GGM. Now, moving on to the algebraic group model, the AGM no longer assumes that cyclic groups are ideal, but instead it idealizes algorithms on cyclic groups as behaving algebraically. What this means is that any algebraic algorithm must only generate its group element outputs by algebraically deriving them from the group element inputs. FKL, the creators of the AGM, formalized this notion by requiring all algebraic algorithms to also additionally output a vector of explanations, explaining how each group element can be algebraically derived from the group element inputs. Then proofs in the AGM can be carried out by reductions, using these outputs and explanations to build solvers for assumed or known hard problems. Now, we pointed out that KZZ had some philosophical critiques with FKL's formalism for the AGM. The most major amongst them was, what exactly separates the group element inputs and outputs to an algebraic algorithm from all other inputs? So let us actually use this critique as a starting point and start building a brand new framework. So let us say in this framework, we do explicitly separate group element inputs from all other bits in the algorithm. So assume we have some kind of an abstract objects to capture group elements, and then we use bits to capture all of the data within the algorithm. Then we can also assume that the bits are free to operate upon, but how do you operate on these abstract group element objects? Well, let us introduce the black box operation functionalities for carrying out the group operation and testing equality on group elements, where the group operation functionality returns a corresponding abstract element object representing the output of the group operation, and the equality functionality returns a bit denoting whether equality was successful or not. But what if you want to do more? What if we also want to typecast out of these abstract element objects? Let us introduce two new black box functionalities called encode and decode, where encode, it takes as input some abstract group element object and returns a bit string representation of the underlying group element, and decode does the exact opposite, taking a bit string element as input and returning the abstract element object as the output. With that, our framework is pretty much complete. Now, we claim that there exists a syntactic hierarchy within our framework. Specifically, we claim that if you use only the operation and equality black box functionalities within our framework, you can capture the class of all type-safe generic algorithms. Additionally, also allowing algorithms the use of the encode functionality allows you to capture the class of all algebraic algorithms. And finally, giving unrestricted access to encode, decode, and all black box functionalities allows you to capture the class of all standard model algorithms. Now, these claims may seem to come a little bit out of left field, but assume for a second that these claims are true. Then take our algebraic group model instantiation in our framework. Immediately, we can see that we resolve all of the KZZ philosophical critiques. Indeed, group elements are explicitly differentiated from bits in our framework. AGM algorithms are indeed algebraic, as any group elements they output must be output as the outputs of the black box operation functionality and in no other manner. And the AGM assumption is indeed weaker than the GGM assumption, since by our very definition, the class of all generic algorithms is a literal subset of the class of all algebraic algorithms. So all that remains for us to do is to prove that these three claims indeed hold, and we'll pretty much be done. Let's begin with claim one, that is type-safe generic algorithms. As I mentioned before, the GGM restricts its attention to the class of adversaries that only interact with the group in a black box manner. So intuitively thinking, what do we really need to build such a class of adversaries? Well, we can begin with any framework computational paradigm to express your adversaries or algorithms. Then all you would need to do is add some kind of an abstract representation for group elements to this computational paradigm, and additionally also include some kind of a black box group operational functionality to operate on these abstract group elements. So let us do this. Suppose you pick your computational paradigm as circuits. Then your abstract group element representation could be special element wires on these circuits, and you could choose special operation and equality gates as your black box group operation functionalities. This becomes exactly the same as the circuit-based formalism as defined by Zandri to capture his type-safe GGM. You could alternatively also set your computational paradigm to pseudocode, in which case your group element representation becomes special element variables, and your group operation functionality can be special operation and equality functions. This is similar to the way that Meyer and Dukas in the past have thought about GGM algorithms. Finally, you could also just leave your computational paradigm as abstract, capturing group elements via indices of some kind of a hidden table and using general black box oracles to capture the operation and equality functionalities. As you may notice, this is exactly the same as Moirer's formalism for the GGM. Now, all three of these instantiations of our type-safe GGM framework are equivalent and can be used interchangeably. Actually, that last statement is a slight lie because as it stands, the circuit-based instantiation of our framework is artificially slightly weaker than the others. And this is because you cannot carry out multiplexer operations in circuit with just the operation and equality gates. So you would need to add some kind of a multiplexer functionality to circuits in order for these to be truly equivalent. But for now, let us assume we do include such a multiplexer and these are equivalent. With that, claim one becomes immediately obvious because as it stands with just the operation and equality gate, our framework exactly matches the existing frameworks that capture type-safe or Moirer's GGM. So we can move on to claims 2 and 3, which is with the AGM and standard model, and we'll tackle these simultaneously. Now, intuitively, these claims also make sense. By giving algorithms access to only encode, you allow them to see the group and the group elements and maybe decide what they want to do, but they still need to derive each group element output by algebraically operating on the black box, on the abstract group element inputs. And by giving them access to both encode and decode, you let them freely switch between an abstract and a non-abstract representation for group elements, thereby all computation is unrestricted, which is exactly the intuition behind the standard model. But let's look at things a little more formally. So let us say we have some arbitrary standard model algorithm that operates on group elements. Now, this algorithm would take its group elements inputs, the bit string representations of these elements, where the representations are known to the algorithm, and would output its group elements also as a bit string representation. Now, an equivalent standard model algorithm in our framework would have the inputs and outputs be the abstract group element objects instead. But this is completely fine since our standard model assumes access to the encode functionality. So we can use the encode gates to build the corresponding bit string representations and run the canonical standard model algorithm internally to obtain the same bit string outputs. Now, in our standard model, we also have access to the decode functionality. So we can simply apply that and achieve the abstract group element representation that we require as an output from our algorithm. So this way, we have shown that any existing standard model algorithm can be represented as an equivalent algorithm in our framework. But what if A was an AGM algorithm? Then by FKL's AGM framework, as I mentioned before, we require that it would also output a vector of explanations. Again, this algorithm in our framework would have the input and output group elements as the abstract group element objects. But again, similar to the standard model case, we have access to the encode functionality. So we can encode the inputs and run the FKL style AGM algorithms internally to obtain the same outputs. But now we no longer have access to decode. So we can't just run that conversion directly. But this is completely fine since we can use these explanations and the input black box group elements to build the appropriate outputs as abstract group elements. And this way, we can also convert any existing FKL style AGM algorithm into an equivalent algorithm in our framework. So the other direction of this is pretty easy to show for standard models. That is, any standard model algorithm in our framework can equivalently be represented as a standard model algorithm operating only on bits. But with the FKL style AGM algorithms, the question becomes a little more non-trivial because we have to ask ourselves, can the AGM algorithms in our framework capture the same class of proofs that the FKL style AGM algorithms capture? Now, as I mentioned before, proofs in the AGM usually are carried out by reductions. And the critical component of these reductions are the explanations that are expected as outputs of the FKL style algorithms. In our framework, we don't really require any explanation outputs, but this is completely fine since we can build an extractor. So what I mean is that for any AGM algorithm in our framework, we can equivalently replace this algorithm with an extracted variant of this algorithm, which does output this vector of explanations. At a very intuitive level, this extracted variant can be built, assuming the circuit-based formalism, by passing each operation black box gate and simultaneously including an addition gate that adds together the explanations of the input group elements to yield an explanation for the output group element. As you can see, this wrapper can be built using just binary gates, which means that it's actually generic and can even be applied to the GGM algorithms in our framework. This point will be actually very important later. So with that, our claims 2 and 3 are pretty much complete and our syntactic hierarchy established. But this might seem a little counterintuitive since we started with our AGM framework to resolve the KZZ critiques with the FKL framework. Now we've already resolved them partially by showing how our framework resolves the philosophical critiques. So all that's left is to take a look at their technical critique, which is the lifting result counterexample. But what is the lifting result in the first place? So FKL, the creators of the AGM, state the lifting result as follows. Take two algebraic games H and P, and let us say the game H reduces to game P via some reduction R. If the reduction R happens to be a generic reduction, and the game H was hard in the GGM, then the game P must also be hard in the GGM, which is the lifting result. Let us look at what this looks like when these are initialized as a straight line reductions using games in our framework. So to derive a straight line reduction from some game H to game P, the first step of this reduction would be to convert the inputs to game H to suitable inputs for game P. Then we would feed these inputs into the assumed AGM solver for game P to derive the outputs, or equivalently, just also use the extracted variant of this AGM solver to get the outputs and the vector of explanations. This would be fed into the second reduction step in the straight line reduction, which would derive an appropriate solution for the game H. Now, assume that the solver for game P was not an algebraic solver, but a generic solver. What happens to this reduction? As you can see, the picture remains unchanged. Inputs and outputs to each of the reduction steps are exactly the same. And this is because we can still apply the extraction logic to the GGM algorithm just as we did with the AGM algorithm. So the reduction still holds. And then assuming that the reduction steps themselves were also type-safe generic, which is the assumption in the FKL lifting result, the entire assumed solver for the problem H becomes a type-safe generic algorithm, which pretty much directly gives us the lifting result. If H is GGM hard, so must be P. But then what about the KZZ counterexample? Why doesn't that work? Now, without going into too deep details of the counterexample itself, the way that the counterexample game works is that they define this binary encoding game, which is hard for an algebraic solver and can be generically reduced to the discrete log security, which is exactly the starting conditions for the lifting result. But then they show an efficient GGM solver that wins this game. Without going into too many details of how the game works exactly, the efficient GGM solver that they build works because they assume that it can output a bit string that it obtains internally as a group element. What that means is that they're assuming that their GGM solver is a Shoup-style GGM solver, whereas our framework restricts attention only to model or type-safe GGM solvers. But this, if this kind of efficient solver was to be instantiated in our framework, you would need to assume that this has access to the decode functionality, which would mean that it's not a generic algorithm at all. But that does beg the question, why do KZZ consider the lifting result from the AGM to Shoup-style GGM? Why not the type-safe GGM? In their own words, the lifting result as stated in FKL's framework only makes sense if you consider your lifting to Shoup's GGM. Why is this the case? Well, let's look back at the straight line reduction picture. Now assume that the reduction step R1 was a type-safe generic reduction and the AGM solver was a FKL style AGM solver. In this case, the outputs of the type-safe generic reduction would be some abstract group element objects, but the AGM solver would expect its inputs to be the bit string representations of these objects, which means that they will no longer be able to communicate with each other, and such a reduction would be impossible. Whereas in our framework, our AGM solver can indeed accept these abstract group element objects as inputs and use the encode functionality internally to derive their bit string representations, which means we can indeed use the type-safe GGM in order to carry out the lifting result. So there we have it. We have shown how we've built our framework. We have proved all three of our claims, and we have resolved all of the KZD critiques, formally restoring the lifting result from the AGM to the type-safe GGM. That's the end of my talk. Thank you.
So is there any comment or question?
Hi, thanks for the talk. I wanted to ask, Can you sort Shoop's GGM somewhere into your framework with the oracles?
Not, so it won't work. So Shoops lies outside of our framework, and that is pretty much because of the way that Shoops deals with representations. So the AGM and the standard model exist in a sub-representation model, which means that they assume that there is some bit string representation for each group element, and that is known to the solver. But the Shoops GGM exists in a random representation model, which is why they can't really communicate with each other. And that's why Shoops is like uninstantiable in this framework, and it lies outside of the entire hierarchy. And this was actually pointed out by Zandri as well in his analysis of Shoops versus models.
Okay,
Thank
thanks.
you.
Other questions or comment?
Yeah, thanks for the really nice talk. So if someone cooks up a new assumption, which model should they be proving a lower bound in? What do you think is the right answer to that?
If you can prove it in the AGM using our framework for the AGM, we can pretty much give you the guarantee that your results will pretty much carry over directly to the type safe or Morris GGM. That's pretty much all we're saying. So if you want to use the AGM, go ahead. Right now, people are a little skeptical with it because, hey, does the lifting result hold or doesn't it? But if you want to now with this framework, go ahead.
And so for the AGM versus Shoop, where do you?
We did analyze existing constructions, and most of them tend to be Morris style GGM constructions. So actually, even though there was a lifting result counter example, it didn't really break any existing proofs of the AGM, which is why people didn't really, take it way too seriously and stop using the AGM all of a sudden. So as long as the thing you're working with does work for Morris, you're pretty much good to go.
Got it. Thanks so much.
Okay, let's thank Deep again. So the third talk of this session is limits on the power of prime order groups, separating Q-type from static assumptions. The authors are George Liu and Mark Chandry, and the speaker will be George.
Yeah, I'll be giving this talk on my joint work with Mark Chandry. Sorry, is this a clicker? Okay. Yeah. So. Oh, okay. Sorry. So to start off, despite the title, we're going to have a little bit of. I'm going to start by talking about composite order groups. So, for anyone who's unfamiliar, they're pretty self-explanatory. They're just cyclic groups where the order is composite. And typically when using cryptography, we want these groups to have the order is typically a product of several large primes. And as such, we can sort of represent these groups and talk about these cyclic prime order subgroups as well. And for a lot of the applications of composite order groups, it's also the case that we'll have these will be in pairing groups. Now, composite order groups have actually seen a lot of use in building like various cryptographic primitives, including types of like encryptions, proof systems, signatures, and a lot more, which could spend a long time listing. And the reason composite order groups have sort of been so useful, at least one of the reasons, is that we have this subgroup decision assumption in composite order groups, which is that if we take elements from certain subsets of subgroups, we shouldn't actually be able to tell which subsets these come from. And this has been useful in crypto because when building some of these primitives, we can sort of undetectably inject noise into some of these subgroups and use that to prove security of crypto systems. So there are also some practical downsides of composite order groups. And the short problem is that compared to prime order groups, they're a lot larger and slower. And this mostly has to do with the fact that in composite order groups, we have to set the order to be large enough so that the modulus is hard to factor. And because of this, we have to guard against sub-exponential factoring attacks, which would break subgroup decision.
So as a result, there's also been has been a line of work on translating a lot of these composite order constructions into prime order groups. And a high level sort of simple example of how this generally works is that we encode these subgroups of composite order groups as subspaces of a vector space, which is encoded in the exponent of a vector of prime order group elements. And now, if we go back to our example on the previous page, if we want to figure out if an element is in this equivalent of G1, then that's actually the same as seeing if this second element, G to the C, is just G to the AB, which is, of course, we can show in prime order groups just under DDH. And in general, there's been this long line of work that's been able to get a lot of features of composite order groups in prime order, in this like prime order translation, using either a DLIN or SXDH. And in fact, this has been so successful that all these primitives that I've discussed before have all turned out to have prime order equivalents. And so we might wonder, maybe it's the case that everything that we can build from composite order groups can be done in prime order via some translation of this framework. So slight spoilers on our talk, we're going to show that this is not quite the case. But to talk about that, we'll first talk about Q-type assumptions. So simply put, these are just some cryptographic assumptions which grow with some parameterized value Q. And typically, these take the form of successive powers or like polynomials of some random variable which are given out. And so the example we'll look at mostly today is with Q strong DDH, which looks pretty similar to something like a regular DDH, right? Except instead of giving out a couple elements, we give out all of these powers of this random exponent x to the q, and we're asked to see if the next power looks like a random group element. Q-type assumptions are also pretty attractive for building some crypto systems because these structured assumptions allow you to build maybe more structured crypto systems which have smaller parameters than you could prove otherwise from something like, say, DDH. But these are also a stronger type of assumption to make because not only maybe you believe that this just looks less plausible in general, but these are also like a family of assumptions where you generally have to believe that these are true for all, like, say, polynomial values of Q. And so because of this, there's actually been another line of work about how to instantiate these Q-type assumptions in composite order groups using subgroup decision, which is, of course, like a fixed size assumption. And using these, we can kind of get the best of Q-type assumptions with their compact parameters while still proving security from a fixed size assumption. And so we could ask, the natural question to ask is, can we show that we can get a similar result in prime order groups? So in our paper, we show that this is not possible, at least in a black box manner. We show that any Q-type assumption can't be reduced to a less than Q-type assumption in regular groups. And this result also extends to bilinear groups where the assumption being reduced to is of a quadratically smaller size. So I know we just listened to an entire other talk on this, but our results are also shown in a generic group model. And as a quick recap here, in the generic group model, right, we're able to interact with the group in an oracle manner. And yeah, the important parts are that you're able to sort of generate group elements and you're able to perform group operations and check equality. So when we're talking about black box reductions, what do we mean? So remember, a reduction is just an algorithm that needs to solve a cryptographic problem. In our example, let's say DDH. But to give it a little help, we give it access to an adversary for another problem. So in our example, let's say it's a Q strong DDH. And using this adversary, it's able to query the adversary, look at it, and as long as this adversary is a valid adversary for Q-strong DDH, then it should be able to use this to break the assumption being reduced to, say, DDH in this example. And what makes it black box is that its interactions with both the group and the adversary that it's given sort of can all be modeled sort of in an oracle manner where it just makes queries and receives responses. So how do we rule out black box reductions between primitives? So if you remember, since a reduction can be modeled in this way of interacting between different parties, we can ourselves have another party which looks at the reduction's interactions with both the generic group and its adversary. And so long as we can simulate these and make the reduction think that it's interacting with such an adversary, it should be the case that if this is a valid reduction, they're able to break the underlying assumption. But if we can do this efficiently, then sort of we've created this self-contained algorithm which can break the underlying assumption, meaning that it wasn't true in the first place. And this kind of technique has been called meta reduction, which was first explored in BV98. So to make our meta reduction, we rely on two main observations. The first is that because when this reduction is querying its adversary for a Q-type assumption, it needs to actually produce a lot of group elements from like a relatively small number that was given from the challenger. And so if we can since we're in the generic group model and we can sort of inspect the queries the adversary makes to its oracle, we can actually see that these group elements come from a relatively low dimension subspace of a function of these input variables. And our second observation is that for many of these Q-type assumptions, such as QDDH, it's actually very hard for these inputs to actually lie in a low-dimensional subspace. So for example, taking our example, since it's a pretty well-known fact that a rank Q matrix of just polynomial evaluations like this, Q evaluations have rank Q, then in order for them to come from, say, a rank 3 subspace, there can only be at most three values of xi for which this is true. So if we put these all together, how does our reduction actually look? So remember, our challenger gives out some challenge, and then whenever our reduction queries its adversary for a particular Q-type challenge, what it can do is it can inspect its queries to the oracle to figure out this matrix M on what exact subspace these H's lie. And since our adversary only needs to sort of work on valid inputs to this challenge, we can, without querying the oracle any further, we can figure out a polynomial set of valid xi values, and then simply check our oracle to see which one it's actually been challenged on. And using this knowledge of the xi, we can break the underlying challenge and act as a valid adversary, which hopefully should allow the reduction to break the outside assumption. And so if we take all of this together, this simulation together, we have a self-contained algorithm which breaks our assumption being reduced to. That's it. Thank you, and I'll take any questions.
We have plenty of time. If you have comment or question, please come to the microphone. No questions or comments? So then let me ask some question. So you said that you have also the bilinear groups,
Yeah.
result on the bilinear groups. So do you treat the symmetric and asymmetric versions of the bilinear groups?
Sorry?
Do your result capture the symmetric pairing and asymmetric
I
pairing?
think it should. We only show it for symmetric. Our paper only
Symmetric.
shows it for symmetric, but I don't think there's any
Obstacle.
obstacles for showing this in asymmetric pairing groups.
So in both cases, you have this square root q minus 1.
Right. And that's just because, you know, if you pair a bunch of elements, you can potentially generate a quadratic number of elements in the target group.
Okay. Thanks. So other questions or comment? So okay, let's thank George again. So the next talk, could we slightly wait so that we synchronize with other rooms? So we start from 9:20. Is there a speaker of the? Oh, so you. Okay. So you are not the. You are not the. Okay, so it's 1 minute before 9:20, so let me call the title. So the last talk of this session is memory sample lower bounds for LWE, and the authors are Jun Chao Yang and Minchi Lu. But maybe the authors couldn't come to the conference, so the talk will be given by Lian Chen. So we still have maybe 20 seconds, but maybe we could start.
Okay. Okay, thank you. Thanks for introduction. Okay, so my name is Lian Chen, and I'm here to talk about memory sample lower bounds for LWE. This is the joint work of Minchi Lu and Junzhao Yang, but unfortunately, both the others are not able to come to Crypto here today, so I'm here to give the talk on behalf of them. Okay, so now let's get started. So, what? Go down? Oh, sorry. How can I get to next? Okay. Okay, thank you. Okay, so the program model that we consider is learning a string, where we have a secret X that is taken some secret space, and we also have many samples that is taken from a sample space. And the learning task is described by a learning matrix that is a function that takes a sample and the hidden secret as input and outputs a label. So the input of this problem is a string that is many samples together with the labels. And for example, it is A1 with its label, A1X, and so on. So for each sample AI is generated uniformly random, and its label is decided by the learning matrix and the hidden secret. So the learner in this problem reads the string in one pass with limited memory, and it is required to output the secret in the end with constant probability. So let's take an example, the problem of learning parity, where the secret and the sample are both n-bit vectors, and the learning matrix is defined by computing their inner product. Okay, so in this problem setting, we measure the efficiency of the learning algorithm by its memory and also its sample complexity. So again, let's look at the example of learning parity problem. We have two true algorithms that give us two upper bounds. Oh. Okay. Okay, so one algorithm is memorizing samples. That is, we just store all samples, which form a linear equation system for the secret X. And then we can just solve X by Gaussian elimination. So this algorithm, it takes square n memory since it needs to store all samples, but it only needs all samples. And another trivial algorithm is enumerating the secrets. That is, we just enumerate all possible secrets, that is all possible 2 to the n secrets, which takes all memory. But as we need to verify if each secret is correct or not, we need exponentially many samples. So given these two easy upper bounds, it is natural to ask a question that if we had any trade-off between these two ones, that is, if we had any algorithm with subquadratic memory but use sample complexity smaller than exponential. A very interesting result by Roth first proved that such trade-off is impossible by information directly lower bound. So this shows that learners with a memory smaller than n squared divided by 25 cannot learn X from 2 to the power of O(n) samples with non-negligible success probability. So this means there is no intermediate algorithm. Any algorithm use subquadratic memory must take exponentially many samples. Given this interesting result, it is natural to ask a question. Can we get a similar information directly lower bound for LWE? As we may believe that any unconditional lower bound for LWE is interesting. So here we consider n as the dimension of the secret vector
and T is the number of samples, and is also the number of rows in this matrix A. So before presenting the results, let's recall the setting of learning with error problem. So in this setting, both the secret and the sample are learned some vectors in ZQ, and we also have an arrow following some distribution. And here the learning matrix is defined also by the inner product by in ZQ. And the error distribution that we consider can be either discrete Gaussian or bounded uniform. So in this setting, the string input is almost the same as before, but here we have arrows added to the labels. And again, the learner is also required to read the string in one pass with limited memory, and it is required to output the secret X in the end with constant probability. Okay, so the result is for LW with modulus Q and error distribution, that is discrete Gaussian with standard variance sigma, any learner should either use this omega k squared divided by a log term memory or exponentially many samples. Here, this k is n times the log term, and here this phi is the Euler function. So how to understand these results? In the standard setting where the modulus Q is a prime number or a product of large primes, this lower bound actually is tight. That is, it matches information theoretic upper bound. And in the other settings, this lower bound is almost tight if we ignore the log factors. And we give additional remarks that one is these lower bounds are unconditional and can be easily generalized to related problems like learning with rounding. And the other is this lower bound can also apply to error distribution of bounded uniform. However, it is not covered in this talk. Okay. So in the following, we give an overview of how to prove these results. So the proof is built on the extractor framework of previous literature. That shows that, roughly speaking, if we can show the learning matrix has some extractor property, which will be defined later, then we can use it to imply the lower bound. However, as the previous work, they only focus on the case of two label, we need to generalize it to Q label case. So this requires us to give a new definition of that extractor property for the Q label case, which is characterized by the Q balance property in this work. And also we need to adapt the previous proof to this new definition, which is the most technical heavy part of this work. And finally, we also need to show the learning matrix in RLE is indeed Q balanced. And there is an additional step that is we need to consider noise, but this step is similar to a previous work that gives a learning lower bound for learning parity with noise problem. Okay, so this is the main component of this proof. And in the following, we'll just go through these components one by one and give a very quick sketch of each one. So the first step we need to do is to generalize from Q label case to Q label case. Let's recall that here our sample and our secret are both learned-sum vectors in ZQ, and the learning matrix is defined by the inner product. So the first naive attempt is maybe we can write down the learning matrix by bits. That is, we write down log Q many learning matrices, where each one output 1 bit of the inner product. Then we may ask if we can directly apply previous lower bound to prove the result that we want. However, this attempt fails because in this case, we need all these log Q many learning matrices to take the same sample at the same time. So if we want to apply the previous lower bound, we found the samples are not independent. So as a takeaway, the previous lower bound in Z2 cannot surely imply our required lower bound in ZQ. Okay, so how to do the generalization? So we do this by recall the extractor property that is used in previous papers. As they consider a two-label case, they assume the two possible labels can be either +1 or -1. So they call such learning matrix as this KLRL2 extractor. If for every f, here this f, it just means a spread distribution. We have at most, okay, so f is a spread distribution over the secret. Then we have at most a negligible fraction of rows A, such that this inner product term is larger than a negligible constant. So roughly speaking, this just means when we take the secret x from a spread distribution, then for almost every sample A, the expectation value of MAX is roughly 0. Given this extractor property, it is pretty natural to extend it into our Q label case, where the output of the learning matrix is in a final set of size Q. So for such learning matrix, we call it Q balance with the same parameters as before. If for every distribution F or spread or over the secret that is spread enough, we have at most a literally small fraction of rows A, such that there exists some I in Q. The difference between this in the product term and 1 over Q is larger than a negligible constant. So the intuition of this definition is when we take the secret X from a spread distribution, then for almost every sample A, the probability of MAX being equal to I is, roughly speaking, 1 over Q. Okay, so now equal with this Q balance definition, the next step to generalize the result from Q label case to Q label case is the following. One is we need to adapt the extractor-based proof to this new definition. And the other part is we need to show the learning matrix in our value problem is indeed Q balanced. Okay, so again, we'll give you a quick sketch of these two steps one by one. For the first step, okay, wait. Okay, for the first step, as we are proving lower bounds, let's consider an alternative combination model that gives the learning algorithm unbounded combination power by limiting memory. So that is the branching program model. And roughly speaking, the branching program is a DAG with many layers, where in each layer we have many vertices that corresponds to possible configurations. So in each step, the learning algorithm takes a new sample together with its label. Then it just transits to the next layer by computing the next configuration based on the previous one and the new input. And finally, when the learning algorithm terminates, it outputs a secret that depends on its last configuration or the last node that it is in. Okay, so here we give a sketch of how to use Q-balanced to prove the lower bound. So we consider the posterior distribution, that is the distribution of the secret S conditional on our learning algorithm reaches some vertex V. You observe that if in the end, our learning algorithm reaches some vertex V with a spread posterior, then it is very hard for it to guess the correct secret. So it suffices to prove that the probability of reaching those vertices with a concentrated posterior is very low. We do this by consider all such vertices. We set it as a target, and we show the probability of reaching the target is bounded by 2 to the power of minus omega n squared. So to bound such probability, this work introduced a measure, a progress measure, that is the similarity, defined as the inner product between the current posterior distribution and the target posterior distribution. Here we bypass the technical parts, but by Q-balancedness, we are able to show that there are two possible cases. For most sample A, when we transit from one layer to the next layer, this similarity does not increase. And for negligibly many A, this similarity only blows up by a small factor that is M also Q. As to reach the target, we need the latter case to happen for omega n times, So we are able to bound the probability by the term that is 2 to the power of minus omega n squared. That is what we want. Okay, and another thing that we need to do is we need to show the learning matrix in elderly problem is in the Q balanced. The work proved this by constructing another matrix M prime. So they show that this matrix M prime has almost orthogonal rows. That is, for most pairs of its rows, they have very small inner products. Then they show that the almost orthogonality of this new matrix M prime implies that the original matrix is indeed Q balanced. Okay, and so from here we can already like generalize the two label case to the Q label case. The next step is to consider noise, which is pretty similar to a previous work on learning parity with noise, and their error analysis naturally generalized to a new setting, so we omit this part. And finally, we give a remark that this result is not tight for LPN, and that is because in LPN and LW, we consider different error regimes. So in this result, the lower bound and upper bounds are depending on these two terms respectively. And we observe that these two terms only match when we consider the error regime of LW. Okay, and that is all. Thanks for listening.
Do you accept questions?
I can try to answer the question, but
Okay.
okay.
So if you have question or comments, maybe no question. Okay, then maybe let's thank Liang again.
Okay.
So this concludes this session. So we will start. The next session will start from 11:10. So let's enjoy the coffee.